Hi, everyone. Can people hear me? Thumbs up? Awesome. So for everyone who is here in person, congratulations on making it through the snow. Unfortunately for us, snow flurries interact a little more than neutrinos do. Uh, and for those of you who are online, thank you for joining us. I hope you're not completely snowed in. If you are, happy shoveling today. We are very fortunate that our speaker made it all the way from the West Coast. Matthias Danninger is an associate professor at Simon Fraser University, as well as a Canada Research Chair. He's on several collaborations. I actually worked with him on Atlas for a time. He's on the IceCube collaboration. IceCube is located in Antarctica. He probably feels like he made a little trip to Antarctica here, except we don't have penguins. He's also on the Gambit collaboration, which is short for Global and Modular Beyond the Standard Model Inference Tool. I think I got that right. So this is software for testing your favorite beyond the standard model theory. He got his diploma in physics from the Technical University of Munich, and then got his PhD from Stockholm University in 2013. And then went on to do a postdoc at UBC, and then started at SFU in 2019. So without further ado, please give an extra loud round of applause to Professor Danninger.
Thanks a lot. I think it's the first time I get an applause before I even start. So if you want, it's of course all voluntary. It's completely anonymous. There's a little bit of audience participation. It's kind of fun. It's like how we teach as well with all these questions. It's just a few questions, maybe 5 or 6, just to sometimes get some feedback as well. Also, if it's desperately boring, you can just bury yourself afterwards in your phone and do whatever you do. So it's a good excuse. All right, so I want to tell you a little bit how to read in the end. There's a neutrino hidden. So about what we call P1, so the Pacific Ocean Neutrino Experiment, and why we are working on this, quite excited here in Canada, and why we think it's a great opportunity to do this here in Canada. A little bit where we are. So we are a pretty new experiment. So we're not up and running. You will not see exciting data yet. But I want to tell you a little bit why we want to do this and where we are. Okay, so if you're set up, so now let's see. Normally this works easy. And look at that. So the question was, what comes to your mind when you hear neutrinos? You can pick multiple answers. And for me, it's just curious to see a little bit what people think of. Especially I like that there's only 10% for not much. So that tells me we can dive right in. So all of these are, of course, interesting. Snow, very famous, very close here. That is excellent. So I will talk predominantly a little bit about the case for neutrino astronomy, because that's kind of the storyline, where to see. There we go. Not too bad. So there's kind of 3 things you can do with these kind of neutrino telescopes. It's not a single measurement. It's quite a multi-purpose experiment. So for example, IceCube does a lot of things. So you can understand neutrino properties, not all of them, but some you can do very well. For example, oscillation parameters, IceCube does an excellent job. Maybe P1 will have a little bit harder time because we go a little bit higher in energy, but I come to that. But we still can work on neutrino properties, sterile neutrinos, these kind of aspects. 2 and 3 is kind of what I want to talk a bit more or motivate P1 a bit more for. This is if you want to probe kind of the cosmic frontier, cosmic neutrino factories, and a little bit want to tell you why this is interesting. And then we can also discover new physics using cosmic neutrinos, potentially. Especially when you think of very, very high energies, you can probably do a quite decent job there. All right, so if I don't want to talk about a history of neutrino physics, because then I spend a whole colloquium by itself. So let me just introduce with the standard model, even if you're not a particle physicist or if you're an undergraduate, I just want to tell you what neutrinos are and where they are in the standard model, and then we just accept neutrinos exist and we take it from there. So here's one of the nice kind of graphics how you can depict the standard model. Everything we know about the elementary particles. So the Higgs is nicely at the center, the last particle we detected. And then we have our force carriers around. So this is how every interaction goes: electromagnetic, electroweak, or weak interaction, and of course the strong interaction. And then we have our building blocks of matter around it, where of course ordinary matter is just done with the down quark, the up quark, and the electron, and everything else is already semi-exotic, I would say. But this is literally our building blocks. And then we have the leptons down here. Everybody knows the electrons. And we go higher up in mass to the muon and the tau lepton. And here are our neutrinos, which are kind of mirrored in terms of these flavors. So we get 3 types of neutrinos in the standard model, and they have each a flavor of the corresponding lepton. And of course, there's an antiparticle to this as well, which for all of these, and this is not shown. So we have the electron neutrino, muon, and the tau neutrino. And we just say they're elementary particle for today, and they exist. And they're postulated in the standard model. In the standard model, they were postulated with no mass originally. We know, not only because of snow and also other experiments, that they do have some tiny mass, but the mass is very, very tiny. We don't know yet what the mass exactly is. We also don't know the ordering of the mass, which one is the heaviest of them. But hopefully we will learn more about this soon. One last comment about this kind of very simple picture of the standard model. So it's not a knowledge or a status of the knowledge we have right now. So this was postulated in the 60s, 1960s. And many of these particles, the W, the Z boson, the tau lepton, the top, the charm quark, the Higgs, they were postulated, the gluon by itself as well, they were postulated at a time where they were not discovered. So it is a theory that had discoverable like objects, and they were all discovered. So this is quite remarkable about the standard model. Also, a bit of a point about the talk today as well. It's very high level. So if we talk about the standard model, this would be what we would have to talk about. This is how everything interacts with the standard model. So this nice graphical representation is obviously a very, very high level picture. And so during the talk, I do very similar things. Of course, if you want to know more, you ask me later on as well, or send me emails. Okay, so here's another question, tough one. So do you know how many neutrinos your body emits per day? Let me get to that question. Here we go. So we have none, or we have an option for 1,000, 100,000, or maybe 100 millions. So don't be fooled by people who type in very quickly. Have your own opinion. So let's see. Let's see if we get a few more people. Some say none. So I think there's a very knowledgeable audience. So it is indeed an order of a few 100 million even. And we emit them during predominantly the potassium 40 decays. So especially if you want to shine very bright in neutrinos in a day, you eat a few bananas, then you will be glooming, shiny, radiative in neutrinos. But overall, these are some of the sources of where neutrinos come from. So generally, everything you see here, they're kind of neutrino interactions trace nuclear reactions. It's also, so if you have a weak decay, you will always produce some neutrinos. So obviously our body, the potassium 40 decay is a weak decay, so we produce neutrinos. Nuclear reactors, the Earth has a lot of nuclear reactions, so we produce a lot of neutrinos. Then we go more to the things we might interesting. So the sun is a humongous source with 100 trillion neutrinos per second, and obviously has been a source which has been used for experiments at lower energies. Not what I'm going to talk about today, but also explosions of stars, supernova neutrinos, and then you can also even go back to the Big Bang, despite that these neutrinos might be exceptionally difficult ever to detect. And we can also produce them in accelerators. We have learned also how to do that. So generally, what is also very important for the talk, so how do we can produce beams of neutrinos? So for some who don't know, this is kind of the symbol for the triumph synchrotron, but you can place any synchrotron over there. So you need to, if you want to produce them in the lab, you want to accelerate some protons. These protons you can then dump into a material, into some target, and you will get a spray of particles. And these spray of particles, they will fly down some sort of decay tunnel, and you can just see literally what comes out. The charged particles, if you don't want them, you can also divert them out of your decay flux and divert them out of your beam. Because essentially what you produce when you dump protons into a target, you produce these positively and neutral charged pions. You don't have to know exactly what they are, but this is exactly the pions you produce. And when they decay, you get a whole flurry of neutrinos out at the other end. So this is how we produce on Earth neutrinos in an accelerator. And the funny thing is, nature does exactly the same thing. We just have a little bit more powerful accelerators. So you need something that accelerates protons. And why not use a supermassive black hole, for example? So huge amount of gravitational energy, it accretes. Neutron stars could do the same. So they accrete mass. You get and eventually where they eject, generally along these kind of jets along the collimator where the rotation axis is, you can accelerate these particles to incredible energies. Then you need your target. The target is a nearby radiation. Can be cosmic dust, can be anything where this object is obscured or anything on the way. So you dump this into this radiation. In this radiation, it's kind of your target. You produce out of cosmic rays plus photons, you can produce neutrons and your charged pions, which give you the neutrinos. And you also will get these neutral pions, and they only decay into photons. So that's, for example, where the high energy gammas come from, which you can observe in gamma ray astronomy. So heaven and earth does exactly the same thing, just that the universe has figured out a little bit more powerful machines so far than what we have done, and probably will remain more powerful than what we will ever be able to do. So if we look at the neutrinos from the universe, how they come from, this is kind of a spectrum. The energy range is humongous. So if you look at this is in electron volts, from 10 to the -6 to above, like what is the 10 to the 20 here? So it's a huge range. So here would be the Big Bang neutrinos, were probably exceptionally difficult, if ever possible, to detect anything down here. There are some attempts, but it's exceptionally difficult. So here we come to, of course, the solar or nuclear. Also, nuclear reactors can essentially produce neutrinos at this range here. So it's the MEV range. This has been successfully used. Snow experiment is one very nice example. And then we come here to the atmosphere. So the same process again. You have accelerated protons, cosmic rays, which dump in the target. This time the target is the atmosphere. And in the atmosphere, you produce the neutrinos in the decay. So these atmospheric neutrinos have often been used also by an experiment like Super Kamiokande. IceCube can do the same for neutrino oscillation experiments. So you can measure the oscillation of how the flavors change when they're produced or observed. So that's also very often used, the atmospheric neutrino spectrum. And then you come to the astrophysical diffuse flux, which I will talk about in a second as well, and then potentially even higher energy out there. But you can see the flux goes down less and less. So you expect very few events. So if we look what has been detected, we have done the solar neutrinos, the atmospheric, and also the astrophysical diffuse flux has been found. In terms of associated sources, there's very few. So we have one, which is a very famous supernova event, which was the first kind of event where you can, outside of our own atmosphere, associate, or our own solar system, associate neutrinos to a source. And also, IceCube has managed to associate one active galactic nuclei with a source. So that's kind of what's out there so far in terms of association. So if we now overlay the observable window where we want to research our neutrinos for P1 or IceCube or neutrino telescopes in general, we come to the tens of GeV range, so very high energy. These are really, really high energy neutrinos, what we are targeting. Okay, so why do we want to do that? It's a very simple analogy. Apologize for that, but I think it's good. So especially today, you could just fall, you hurt your hand. So you go to the doctor and the doctor can not much tell because you just have a visual inspection of your hand. But luckily to us, we have now different spectra, what we can use also at the doctor. You can go to X-rays, you can go to an MRI, and maybe the doctor very rarely uses infrared to see where your hand is the hottest or the coldest. But the point of this is whatever kind of different observation tool you have at hand, you have learned something new. In medicine, hear about your injury, and you can do exactly the same if you observe the universe. So this is just the electromagnetic spectrum, how we can, for example, look at the Crab Nebula. It's a very famous object to look at. So from radio, infrared, over visible light, which is of course not a true color image, then we can go up in energy to ultraviolet, X-rays, and gamma rays. So at each time, you're able to see this in a very different way. So infrared or visible light. So infrared, you can see more the synchrotron radiation. So this is where the electrons get accelerated in these magnetic fields. Visible light is more the remnants, how this supernova explosion eventually happened or happened prior. And then if you go to higher energies, eventually you see something very new. In X-rays, I think it's probably the most impressive picture here. You can start to identify the fast rotating neutron star, where the matter kind of is co-rotating around in this disk, which is slowly falling in. And then you have these two jets which are collimated along these axes, which are sort of coming out, which you can start to see. And then if you go to gamma rays, so the highest energy photons you can observe, you only see the neutron star essentially radiating high energy gammas. So the question, of course, is what can we do there with neutrinos? What can you learn? So this is the analogy why this is very interesting to also try to do astroparticle physics and also astronomy with neutrinos. Also, if you go even further than this, there might be, let's say, 20 to 25% of the universe we have actually not even looked at all. So again, we have the same energy range, goes even a little bit higher here. So this is a huge energy range. This is also a distance now in megaparsecs. So here would be our galactic center, nearest nearby galaxies, and you go to cosmological distance on the y-axis away. So usually we use here radio, infrared, X-rays. Again, you go higher in energies, gamma rays. Then we have neutrinos and cosmic rays to tackle the high energy part. The interesting thing is that this whole part of, let's say, the high energy universe is completely opaque to photons. So everything we ever seen in astronomy or observational astronomy, high energy gamma ray observations, is all in this white area, region. So there's around 20% of the most energetic and also distant universe. We have no idea what's hiding behind it. And you need a different messenger to essentially try to probe this. Also, maybe we talked about this with some colleagues today a little bit. So remember this kind of energy range here. So 10 to the 17, maybe close to 10 to the 18. So I'll come back to that. But you can see here, we are definitely sort of in this energy range where there's a lot of black. So unexplored phase space in terms of energy and distance. All right. So one more question. So when I talk about neutrino astronomy in a second, what do you think is the most important attributes of the neutrino that you can do neutrino astronomy with? So that it is electrically neutral, essentially cannot be absorbed, it's essentially massless, or that it tracks nuclear processes. Don't know, this doesn't seem to show up. Yeah. Maybe it's a secret survey. This one is a secret survey. So I don't know what, we will skip that then. Come back to it afterwards. So essentially all of them are equally important. So if we compare our three messengers, let's say what we know of. So we have photons, neutrinos, or charged particles, and they're emitted from some distant source. So the reason protons are pretty good, but they're charged, and you have a lot of magnetic fields in the on your way from your emission to wherever you're going to detect it. So you lose essentially the crucial information from where they come from. The higher you go in energy, it's sort of, you can sort of do some directionality, but you still never know exactly where they were emitted from. So you can never point back and do essentially astronomy with this or study sources or distant sources. Photons, on the other hand, have been studied and used a lot. But of course, when they're emitted, they can get absorbed. They're usually re-emitted. They carry different information. They can be so-called redshifted. So they lose a lot of energy. So you actually don't really know what comes to you. So it's kind of, it's still, so far, I would say, the best messenger we had. The one I'm not showing right now is gravitational waves. Maybe I should update this. They should go on this slide as well. But then the neutrino doesn't really care because it just goes through literally everything. So it is, to some degree, the perfect messenger. So it's electrically neutral. So magnetic fields don't do anything. It's essentially massless. So it travels very fast. It is essentially unabsorbed. And it tracks nuclear processes, which is exactly what you study. So photons, high energy photons, you can create from many different, for example, you can accelerate charged particles. They, like we do on Earth, and then they just emit photons. So you never know, is there actually a nuclear process happening in the start? Is there acceleration of hadronic material in these active galactic nuclei? You will never be able to study this just with photons. But of course, these cases make it also very, very difficult to detect. So as beautiful as it is as a messenger, the messenger you can't capture is also very tricky. So how do we do this? For neutrino telescopes, we go to large bodies of water or ice. So if the neutrino comes in down here, it undergoes a charge current or neutral current interaction. So it depends a little bit how this interaction looks like. In this case, it would be a charge current interaction. In this interaction, you can produce an electron or a muon. You could put a tau lepton as well. But if, let's say, it's a muon, this muon can travel a very, very long time because it's very highly energetic through your water or your ice. And as it travels faster than the speed of light in that medium, it emits something that is called Cherenkov radiation. This Cherenkov radiation sort of can be a little bit compared to if an airplane is supersonic. So if an airplane is supersonic, it has a very characteristic sound wave, which comes at a very distinct angle. And this is exactly a very distinct angle you can observe also for Cherenkov radiation when it goes through. So the only thing you have to do, you basically distribute your detector. It's a lattice of sensitive cameras, of optical sensors into the ice or into the water. And then you can record the time and the amount of light you see in each of them. And from this, you can reconstruct the path of your charged lepton. And because of these very, very high energies, there's almost no angle between the neutrino and the lepton which is produced. It's a very small angle. You can infer back the direction of the neutrino from where it came from, and you can do with this neutrino astronomy. So the motivation for P1 is literally IceCube's legacy. And Miriam said before, I am on IceCube. I'm not on IceCube. I was on IceCube. So I don't want to claim anything that has been done since 2014 or 15. So since then, IceCube is successful. Since I left, that's the time I joined Atlas. Atlas discovered the Higgs before I joined. So it's kind of a, so yeah, you can see the success rate for IceCube, for P1, where you're gonna go. So for those who don't know what IceCube is, it's just to scale. And it's also a reason where I could put a nice picture of myself building IceCube. So IceCube is at the South Pole. And I just put that picture here for scale. So these detectors are humongous. And it's very hard to imagine the size of the detectors. So this is the footprint. It's not exactly a cube. It's a hexagon, but it's around 1 square kilometer. And then the ice is nearly 3 kilometers deep. And the bottom 1 kilometer of this is instrumented with these detectors. It's always quite amazing. Also, when we had collaboration meetings for P1 in Philadelphia, and you look at big American buildings, I can do the same here. They're 200, 250 meters high, tall buildings. And then you think you have to go 4 times this to have one of your detector lines. It's huge when you think about the size. So IceCube uses ice and has been exceptionally successful. And I want to just show you a few like motivations why we do what we want to do. So the first thing you look for if you want to look for astrophysical neutrinos is something you look diffusely all around you at high energies. So it is, first of all, you will see in your energy spectrum of neutrinos, which are sort of, these are the reconstructed energy of the neutrinos. Here is just counting neutrinos. So if you integrate over time and you look at the energy, and you compare this with all these shaded areas, which is, let's say, your background expectation from what is happening in the atmosphere and what you can think from your atmosphere, then if they are out there, they expect to be more energetic, you will start a deviation of the spectrum to higher energies. And this is exactly what you can see here. So these crosses out here, and the thick red line is sort of an astrophysical, best fit to an astrophysical neutrino spectrum. So this was discovered first, actually, when I was still in IceCube in 2013. We started this, and by now it's 10 sigma, and it's in all different neutrino flavors. That's why I put this back here. So this is quite relevant. So this one is shown here for electron and tau neutrinos, where we have 2 dominant channels how you can detect them in these experiments. One is kind of we call it a shower-like event. So this happens for electron neutrinos or for any scattering of neutrinos. So when this interaction happens, you have a very localized, very spherical shower-like topology of this interaction. So this is the light, how it is spread out. If you create a muon, then muon is traveling for sometimes kilometers through the ice or through the water and emits light along. So this is what we call track-likes. So this analysis, what I showed here, is for a shower-like. It is also has been seen, this was actually how it was first seen for the muon for the track-like events. The track-like events is what you have the pointing back really well to some origin in the universe. And then these would be the tau neutrinos. They're double peaked because you create a tau lepton. The tau lepton is very short-lived, so it travels a little bit through the ice and decays again. So you have kind of a bang, bang. It's like called double bang. So very hard to identify. IceCube has, in 13 years of operation, 7 likely high-energy tau neutrino events. But it is important that you can do with these detectors at these very high energies particle identification, and you can see all neutrino flavors. So this enables you to do a lot of different physics and also study the neutrinos at very, very high energies. Then what else have we learned? That we have seen this astrophysical neutrino flux. So this shows you, again, energy. It's always the same down here. Here's a flux. So what is for my colleagues here, so this is where the LHC beam energy sits, but they know, of course, that the universe can be much more energetic, but it's just for a comparison of what the energies we talk about here. And the y-axis here is it's quite complicated, but it's essentially an energy density, or how much of energy is the universe sending to us every second when you observe. And the interesting thing or conclusion from this, what IceCube has basically determined here, here's our photons, what we use to observe the universe forever. Here are our high energy charged particles. So you can see the scale is the same. The same amount of energy reaches us from these messengers in the universe. But you can see the neutrinos, despite very badly measured because it is so hard, has the same scale. They also have to when they are linked in production. But it is a very important piece of information that you can do the same amount of energy in principle is reaching you every second. So now the question is, can you tap into this and then study this in the same way that you can use this for studying your universe? Once you have established that astrophysical neutrinos reach us, IceCube has established that there's so far 2 or 3 sources, what they have found. So one, for example, so this would be a sky map. So you look at all the neutrinos at high energies. Do they cluster up from somewhere? So this is then likely they come from a certain active galactic nuclear or something else you can think of. So this one here, for example, is after like 10 years of observation. You can see when you look now close to the source here. So this will be where the source is. You can see this is the expectation from the background, and it rises and gives you this kind of excess of neutrino events from the source. Why I want to show this here so explicitly IceCube has squeezed every machine learning technique, everything out of this to get this precision here. So this is after 10, 12, 13 years. It's a really great achievement. But just imagine you could halve this precision, then you need to wait less long. Or if you can be way more precise, then very few events down here basically piling up will help you to identify more sources. So if you be more precise, you would see way more sources or faster. It's kind of a bit the takeaway. The last one, which I'm going to go a little bit quick. So the galaxies, of course, our own galaxy is very interesting as well. Do we have neutrino sources in our own galaxy? You can play the same game, what I said before, with pions. So we have the optical observation. Maybe you've seen from NASA these multi-wavelength pictures where this kind of comes from. So this is optical. These are kind of high energy photons. Then based on the prediction of the high energy photons from these pions, you could have a prediction where would you see neutrinos. And then IceCube has kind of seen the neutrinos. So it's sort of 3, I think 4-ish sigma. It's a very hard game for IceCube because IceCube is located at the South Pole and the galactic center is above IceCube. And these neutrino telescopes work by looking down into the Earth generally. So the location in this case matters a lot. But nevertheless, it's a very interesting thing, and this makes the motivation that you want to study your own galaxy. So what we want to do, we want to build on this legacy because IceCube has shown it's out there. The potential of this field is there. But IceCube is also, after 12, 13 years of running, it just doesn't have enough events. So you want to push this frontier. So we want to discover new and more sources. We want to resolve the neutrino sources in our own galaxy. So the known sources, the 3 they have found, contribute only 10% to the diffuse flux they have seen. So there must be many, many sources out there to make up this flux. We want to study the neutrino. We want to use these neutrinos also to look for new physics, and then contribute, hopefully, to a global network of neutrino telescopes. All right. Question, how many neutrino telescopes exist or are under construction today? What do you think? Let's see if it actually works. Otherwise, we skip these questions. Hi, look at that. So we have 1 or 3 or 7. So far, Toronto has been exceptionally knowledgeable. Let's see if this continues. I see this question is a tough one. The knowledge level goes down. So IceCube, yes, is 1. So there are actually currently 3. 7 could potentially soon be happening. So here is a map of kind of the neutrino landscape. So IceCube is at the South Pole. KM3net is here, is in the Mediterranean Sea. They're under construction. And in Lake Baikal, GVD is also a neutrino telescope which exists to a certain size. So we are here in Canada. We try to come like into the game here, and then as everything in science and especially in particle physics these days, so China is not only proposing 1, they want to build like 3, and of proportions of never seen scale. So it could be that tomorrow there are 3, or we don't know. But it's certainly they have very, very high ambitions to also build very large neutrino telescopes. So if you have followed maybe something or seen a press release, I just wanted to comment on that. So yesterday there was a webinar and a press release and a paper in Nature about the highest ever neutrino event observed by the KM3net collaboration. So that's why I pointed out this error of energy before. So the claimed energy is 220 PeV, exceptionally high. The second highest event ever seen is from IceCube is 10 PeV. So this is a factor of 20 higher. So you can see it's a partial detector. It's much smaller. It's still quite big if you look at compared to the Eiffel Tower, but it's a small detector compared to IceCube they're building currently. Also, they cannot point back enough because they don't know exactly where the detector right now is. I'll come back to that in a second. They can point, but not as precise as they would need. So I'll bring that back when I talk about P1 in a second. Okay, so finally, so what we want to do, we want to partner with, or we are partnering with Pacific, or basically with Ocean Networks Canada, which, if you've never heard of this, is the largest undersea real-time observatory that exists in the world. So it actually has also here on the East Coast a lot, but mainly the main part of it is on the West Coast, and some is also up north. So the main part is this huge cabled loop they have. It's called the Neptune Observatory. It's an 800-kilometer long optical fiber loop. So it provides at 6 different nodes, which are placed around here, around 8 kilowatts in power. And here's 2 gigabits. It can be pushed up to 10 gigabits of data transfer as well. So essentially, if you want to build a new neutrino telescope and you need this deep underwater infrastructure, it's like going somewhere where you can plug in with a power plug your detector, and you Ethernet cable, and you just run your detector. That's kind of the idea of this business. So we want to go here to the Cascadia Basin. It's nearly 3 kilometers depth in the water. And this is just in the moment an image, whether it's clustered or uniform. But the goal, the vision, is to build a qubit kilometer detector, so of the size of IceCube. Why we think we can push the field even with a detector of the similar size, I will show you in a second. So the key is for P1 to not just build big. We want to build, of course, big, but also to focus on the precision, because precision is something that IceCube has basically run against the wall to get any further. So what you see here is the same muon event. So this is a muon going through, emitting these Cherenkov photons in a detector, which is IceCube. You can see these lines of detector here. On the left is in ice, and on the right is in water. So the photons in color is like early photons and late photons. And the main part of it is here in ice, photons live much longer. They're not absorbed. So the absorption length in this ice in the, does it do it again? We can just do it again. In the super transparent ice, it scatters around, but they live a very long time until they're absorbed. In water, the absorption length is shorter, so you lose photons faster, but the scattering length is enormous. So you see every photon is essentially emitted and goes directly to your detector. It doesn't take any deviation. So when you want to reconstruct the precise track here, this is the information you need, because ultimately here, the scattering, this wiggling around this time, how much, or the distance, what it is from where it is absorbed, limits your precision in how you can reconstruct the lepton and therefore reconstruct the neutrino. That's why water is a very, very interesting medium to do that. So what IceCube wants to do potentially is build bigger. So generation 2, they want to increase the volume and just build bigger, if it is possible. What we want to do, we want to use new technology and really make it precise. And you can get, for the same size of detector, if you manage to push down by a factor of 4 or 5 the precision in how well we can reconstruct the direction of the neutrino, then you can achieve a factor of 10 improvement in being able to see sources. So this is this order of magnitude for a new generation detector you always want to achieve. So what you see here is a bit technical. Here's the angular resolution for muon tracks, and here's the angular resolution for these cascade-like events. Because actually out of this blob, you can actually get a directional information, because it is not a fully spherical blob. It's a blob which is basically time dependent. It also moves a little bit. So if you detect these photons, you can also get a directionality out of this. So this is currently best IceCube. So this will be what we can do, or hopefully in our simulations can do P1 at trigger level. And this is what we want to do to really push down, if we assume the same candidate events what IceCube has for this line. So we want to push down in this precision to do this exceptionally good angular resolution. For cascades, you win a little bit differently. So here is IceCube currently. The ice is really limiting them with the scattering. And you push down here for the readout threshold the way the KM3net detector is designed. And with the technology we want to use, you can in principle do another factor of 2. So this is the idea. What we want to drive with P1, similar size, but different precision. So what have we done? We have done pathfinder missions between 2018 and 23. I will talk about them in a second. So these are 100 meters. These are 450 meters tall. This is currently what we are building on. So this is, we hope to get the very first detector line into the water in fall this year. I will show you pictures how this looks in a second. We are a funded project of somewhere between 7 to 10 lines, depending how well we can budget this. So this is what we call the demonstrator phase. So after this year, will probably take us 2 years to build the rest of the lines and put them into the water. And then from there on is what we want to build. If this really works the way we want to, of course, we have to demonstrate the precision you can demonstrate, the reliability, what we want to achieve, and also simply the operation with Ocean Networks Canada. Then this is essentially the goal afterwards. So for the Pathfinder missions, what they were essentially the main part, here you see some images with Ocean Networks Canada, which is a big, big plus of this detector. So normally you don't want physicists trying to do the underwater cabling, the infrastructure in the water. It's a huge, difficult engineering problem, and lots of experiments have failed at this level. So the idea to partner with the people who know what they're doing and have a very reliable track record is one of the strengths of P1 and the project. So here you see some images. So this is how the remote operated vehicle then connects all these lines. And you can always watch this on your screen and how it happens in real time. It's quite impressive. So one of the things which was very important from the first mission of the Pathfinder is that ONC is actually reliable enough to operate such a detector. So unlike, for example, the LHC, where you know exactly where your beam comes, so you can make sure that your detector is on, you never know when something interesting will happen. So IceCube has achieved 99 point something of uptime, and it's very important for these detectors because you don't want to miss something. So with ONC, over a few years, we managed like 98% operational uptime, and that's very, very important. Because if that is not good, then you also can't operate a detector reliably. Also, the optical properties are very important. So this is kind of here shown, the attenuation length over the wavelength. So here you see sort of KM3net. Our measurements are the black ones, which are a little bit lower, but also we were very far at the bottom. But even the black measurements are yielding a very, very good optical properties for running a neutrino telescope in these kind of waters. So for reference, for example, this is what the Lake Baikal is significantly more, let's call it murky, maybe, or full of sediments. So we understood also the potassium 40 background. It's a big background, bioluminescence, sedimentation, and then you also have to take care of biofouling. So you can see a little bit here, some of the modules, whether they were oriented up or down, came out of the water after a few years, significantly more shiny than some others, which had a significant growth of biofouling, what we call it. But this is well understood, and we have plans to also mitigate this completely. Okay, so I'll speed up a little bit on this. I wanted to show you. Let me skip that question for the sake of time. What our concept is, and then I'll skip a few details on where we are. So one of the things what we want to do different is we want to build a very reliable system, which is very, very precise and incorporates the latest technology. So IceCube was perceived 15 to 20 years ago. Times have changed quite a bit in terms of electronics. KM3net is already a detector which was 12 to 15 years where the concept, they have improved already on IceCube. So you want to use all these new technology which is available. So we still use PMTs, but I'll come to that in the next slide. So we will have 1 kilometer long mooring lines with 20 of these optical modules. We aim for a connectorless design, which is the weakest point. So of course there are connections, but not penetrating connectors through the glass. So inherently, when you drive high current through salt water, it's a very, very challenging problem. And it's the single biggest point of failure of all of these experiments. So what we try to do is we have a system which is essentially terminated in these exceptional, secure, onshore, secure terminations, and we have no penetrators. So we have nothing penetrating essentially our detector units. I mean, to some degree, this is penetrating, but it's onshore sealed off, which is very different to a glass penetrator, which is penetrating directly through a cut hole in the glass. So we have a lot of calibration, which we'll show you some in a second. We have a sub-nanosecond time synchronization, which for LHC sounds slow, but for these kind of detectors is kind of very fast. And we have a new mooring line infrastructure, which is essentially at the bottom of this line. You have kind of a little computer sitting every time and kind of operating this line, each of them individually. So here are some details about the optical modules. We use these small PMTs. So these are our photo detectors. IceCube uses one very large PMT. So the more segmentation brings you more precision. And also you can veto against various coincidences. It's a very modular, very simple way actually to build it. The optical coupling is done with a gel pad. So you can see sort of little images here. And then some of the highlights here. So all of the readout of these 16 PMTs is a full waveform digitization, which is very important because then you get the precision to identify which neutrino flavor you have seen. And all of this is a huge advancement in computing essentially over the last few years. It would have not been possible 5 years ago with the power budget and the data budget we have available down there in the ocean. It's kind of in time, you can build newer things. So here's some images. So this is in Munich where they are assembled at the moment. We have already more of them. They're essentially ready to be shipped to Triumph. So here the main board is missing. So this is kind of what we call an interposer board where everything is channeled, which essentially drives all these PMTs if you look a little bit inside. So then calibration is really, really important because if you want this precision is only possible if you understand absolutely everything. One thing, this first line is probably entirely over-designed, but you need to know the optical water properties exceptionally well. You need to know them depth dependent. You need probably the absorption and the refractive index and the scattering depth dependent, time dependent. You need to constantly monitor it in order to understand exactly if you want to achieve this precision. Even if the refractive index changes with pressure, what it does, you need to be able to measure it because it's kind of the group velocity of light. And you need to know then, if you want to achieve really this precision, you have to have a control over this and measure it to some degree. The way we want to do this is essentially with little lasers. So we shoot laser pulses up and down, and they're very short, they're very sharp, at many different wavelengths. You can shoot them up and down. And as I said, we go overboard. We shoot them also out in the water, but that of course helps if we have multiple strings. And by being able to do this in multiple wavelengths, we have essentially shown in studies that we can measure to the degree we have to understand the water, we can understand the water. So here's just how these would look like, kind of assembled on the side. Here's in the lab at SFU, quite a few of these laser boards we have designed actually together with HyperK. So it was a nice collaboration. They use the same boards. We use a higher power version. They use an even faster laser board. So we are building 400 of this for the first line, which is, as I said, a little bit over-engineered to do. What we also do, we have special calibration modules. These will be probably 2 for the first line and then 2 per line. So it's kind of hybrid. We still have some PMTs, so we can do some science with them. But the kind of poles are taken out. No PMTs are there. And we have this kind of light bulb here, which is optical Teflon, is a diffuser light bulb. We put 5 lasers underneath. And the idea is that if you put both sides together, which you can see on this plot, and you go a little bit away, so from 3 to 4 meters, you essentially have a fully isotropic light source, which flashes a different wavelength very, very fast. And it's very bright underneath here. So you can see kind of here, it's almost uniform if you look over the whole spectrum. And we can reach up to 300 to 400 meters into the water with these lasers. So this will be also used for the calibration and hopefully also position calibration later. There's a lot of details here, which I want to skip, but they are self-monitored because you need to know if the lasers age, if you have absorption on them. So we have an internal self-monitoring of all of these consistently. So here you see a few of these things. So this is, again, also a collaboration with HyperK again. So they have nice water tanks where some of my students try to test some of these modules. Here you can see one. This is obviously not a laser. It's just an LED light. That's okay. Yeah, that's all right. I'll be fast. And here you can see how this looks with a camera object, sort of if you rotate this around, how this light source would look like. So because of time, what I will skip is the acoustic system, despite it's very interesting. If you want to ask me about it, please do. So we had to build an acoustic system. I said before already to some colleagues, I never thought I'd do acoustic science. Because when these sway in the ocean current, we need to understand where the detector is in order to be able to reconstruct. So this is what we have built. So we tested this. I show you some pictures here. It's a lot of fun. You can go on the ocean as well. And it actually works really well, which I will skip here. So what we have shown compared to a commercial system, which is like $500,000, which we took into the water, we can achieve essentially a precision of like 20 to 30 centimeters per detector module at the moment. And that's kind of what we need to reach to make this work. And this is also where KM3net currently, where this comes into place, where the precision of this super high energy event was not enough. They actually technically didn't know where the detector is really oriented. So this is something very, very important, because otherwise you can't do precise science. Okay, so just to show you how this thing will look in the end, this is what we're trying to put together at Triumph. So basically all the cable will be kind of on this deployment frame, coiled up with a float on the top. You drop this, so as simple as it is, you drop this into the ocean, an ROV goes down, connects it in, pulls a plug, and then everything just unfurls perfectly. And then it will operate fantastically without any faults. So that's the goal. What we do, 2 more slides, then I'm done. So this is a bit of an older map of the collaboration, but essentially currently at in McArtney in Denmark, the cable and the titanium breakouts are being designed and engineered, and will be on this tray, will be shipped to Triumph. In Munich, all these detector optical modules are being done. Every calibration device and module and detector is built at SFU, and some electronics in Alberta. The main board is built in MSU. And then eventually we do the final integration April, May, June this year at Triumph. And then it goes onto the ocean and into the water, hopefully in September this year. What I don't have time right now, because I ran out of time, please ask me at coffee if you're interested. This array has a huge amount of possibilities for ocean science, climate science, which is not our core expertise, but it gets a lot of people very excited and also does help with the funding. I will skip through this. I had 2 examples why this is interesting, but I will skip through this. And you can tell me this later. What do you think of P1 now? So here are a few of us at 2 collaboration meetings, and thank you for your attention.